Hi everyone. I want to talk a little bit about the equations of kinematics for constant acceleration. Hopefully you've begun to discuss this in the lecture part of your course, but if you haven't, I'll talk about it now because you're going to be using it in the projectile motion laboratory. So let me introduce them here. These are the equations of kinematics for constant acceleration in one dimension, say in the x direction. They are simply equations that relate parameters of a path from point A to point B. If you know some of those parameters, you can figure out the others, if the object is accelerating at a constant acceleration. The parameters that they relate are x, the amount of distance it travels from point A to point B, Vx naught, the initial velocity in that direction at point A, Vx final, Vxf, the final velocity in that direction at point B, Ax, the acceleration in that direction, and t, the amount of time it takes to get there. So there are a variety of problems that you'll do in these kinematics problems in the lecture part of your course, and you're going to use this in 2 dimensions in projectile motion. Let me start talking about 1 dimension, then I'll quickly shift to 2 dimensions. So let me give you a few examples of a problem like this. Let's say you have an object sitting at position 2 on this axis, and it's initially standing still, and it's going to accelerate at a rate of 2 meters per second, 2 meters per second squared, for 3 seconds, and you want to know where it's going to end up. Okay, so which things do we know? Okay, we know the acceleration, 2 meters per second squared, right? What else do we know? I said it's going to go for 3 seconds. That's the time. Right, and what else do we know? Well, I said it's initially standing still. That means Vx naught is 0. Right? And what do we want to know? Well, I asked how far will it have gone after 3 seconds. X is what we want to know. So we got to find one of these equations that contains those 4 variables. 3 of the ones that we know, and the 4th we want to find out. So which equation can we use? Well, let's see. This is the variable we want to know, right? We do know this, that's 0. We know time, but we don't know this one, right? So we can't use this equation. What about this one? Well, again, we don't know that, and x isn't even in here anyway. What about this one? That's what we want to know. We know that, we know the time, we know the acceleration in the x direction, we know the time. So we can use this equation. So let me just rewrite this. So we want to know that one. This is 0, 3 seconds, plus 1/2, 2 meters per second squared. And this is 3 seconds squared. So this is 0. This is, let's see, 3 squared is 9, times 2 is 18, times 1/2 is 9. And if you look at the units, this is going to wind up in meters because there's seconds to the minus 2 seconds to the square, so that's going to wind up in meters. So it's going to go 9 meters, so it's going to wind up at the end of there. Okay? So you see how that works? Let me do one more problem in 1 dimension, and then I'll switch to 2 dimensions, and you'll see how that's going to work for this lab exercise. Let's say I have a particle that's initially moving, and it passes the 2 meter point. It's initially moving at 4 meters per second. Write it that way. And let's say the acceleration is 3 meters per second squared. And I want to know how fast is it going to be going when it crosses the 10 meter point. So that's what I want to know. So now I've only got 2 things over here, but I said when it crosses the 10 meter point, how fast is it going? So I also know x, the distance that it's traveled, and that's 8 meters. Right? Okay, so which of these, so we got to have an equation that contains all 4 of these. So which one can we use? See, x we know, that we know, that we want to find out, but that we don't know. We don't know the time that it takes to get there. What about this? Again, we don't know the time, and we want to find out that, but we don't know the time. Again, we don't know the time, but look down here. That's what we want to know. We know that, we know the acceleration, we know how far it's traveled, so we can use that equation. So let me write that. Okay, so there's what we want to know. This is 4 meters per second. And the acceleration is 3 meters per second squared. And it's going 8 meters. Okay, so 4 squared is 16. And remember, the units get squared too, so that's meters squared per second squared. 2 times 3 is 6, times 8 is 48. And the units get multiplied, meters squared per second squared. Okay, 16 plus 48 is 64 meters squared per second squared. And that's the final x velocity squared, so if I take the square root of both sides, 8 meters per second. Okay, so now you have some idea how these equations work. So now let's quickly extend this to 2 dimensions. A 2-dimensional kinematics problem is where an object goes from point A to point B, but it travels in not only the x direction, but also the y direction. It travels in 2 dimensions, and there's constant acceleration in each dimension. So I've written the same equations of kinematics for the y direction. It's just the same equations as these, but for every x over there, I've replaced it with y. So now the parameters in the y direction are y, the distance traveled from A to B in the y direction, the initial y velocity at point A, the final y velocity at point B, the y acceleration, and time. Now, this may seem like it's a lot more complicated, but it isn't that much more complicated because these 2 dimensions being perpendicular to each other, the x forces don't affect the y motion, and the y forces don't affect the x motion. So they're like independent problems. They're like 2 problems that are going parallel to each other. And notice, there's one parameter that's the same from the x direction parameters to the y direction parameters, and that is t, the amount of time it takes to go from A to B. The way these problems usually work is you know 3 things in one dimension, and you use those to find time in that dimension, and then you take time over to the other side, and then you'll know 3 things in that dimension, and so you can solve it in the other dimension. So it's like 2 problems that you do in a row to solve this problem. And that's what we're going to do in the projectile motion problem. Okay, so let me state this 2-dimensional kinematics problem. It's this projectile motion problem, and then we'll set it up and then we'll solve it. So let's say I have a cannon firing a cannonball. It's at the origin, and it's going to fire the cannonball at 8 meters per second. And it's going to fire it at an angle 65 degrees above the horizontal. And what do I want to know in this problem? I want to know where it's going to land. This is level ground, so it's going to just move in the x-axis. I mean, it's going to move in the y direction and then come back and land on the x-axis. So I can solve this problem using 2-dimensional kinematics. So let's write down some of the things that we know. Now, since we know the speed that it's going in that direction and we know the angle, we can actually figure out the initial x and the initial y velocities. I'll do that in a minute. That's hopefully something you've done using trigonometry in your lecture part now, but if you haven't, I'll show you how to do it quickly. So we know both these things. We also know both the accelerations, the x acceleration and the y acceleration. The y acceleration, this is a cannon on the Earth, so the y acceleration is the acceleration due to gravity, minus 9.8 meters per second squared, right? The x acceleration is going to be 0. Because we're saying there's no forces in the x direction. It's just going through the air, and so there's no forces in the x direction, so there would be no acceleration in the x direction. Now that's not quite realistic. In the real world, when you fire a cannonball through the air, there's air drag, right? So that's going to act in both directions, but that makes it a more complicated problem. So let's do this simpler problem first where we can ignore air drag. Okay, so we know both the accelerations. And then I said that we want to find t in one of these dimensions so that we can eventually find x. And as not surprisingly, we're going to find t in the y dimension and then use t in the x dimension to solve that problem. But I said that we need to know three things in one dimension in order to find a fourth. We know that and that, but what else do we know in the y direction? Well, notice it takes off from y equals 0 and it comes back to y equals 0. So the movement in the y direction is 0 meters. Does that make sense? If I was firing this cannonball onto the top of a 5-meter building, then y would be 5 meters. If I was shooting it down into a valley, then that's 10 meters deep, then y would be minus 10 meters. But in this case, it's 0. Okay? So, so this is the stuff that we know. Now let me calculate these. So velocity is a vector quantity, right? And you can break it down into the component quantities. Here's 6 meters per second in the upper right direction. We want to know the x component of the velocity and the y component of the velocity, right? The initial velocity. And this is 65 degrees. So you can treat these values just like the sides of a right triangle where the hypotenuse is, whoops, I'm sorry, that's supposed to be 8 meters per second. Sorry about that. So now you know that the in trigonometry, the adjacent side over the hypotenuse is the cosine of the angle, right? And the opposite side over the hypotenuse is the sine of the angle, right? So Vx naught is 8 times cosine 65. Vy naught is 8 times sine 65. And those turn out to be, let me just write them up here, where I've got this. This is 3.38 meters per second and 7.25 meters per second. Okay, so this is our two initial velocities. Now I'm prepared to solve this problem in the y direction and then go over to the x direction. Just get rid of this. So what do we know? What do we know in the y direction? We know the initial y velocity, we know the y acceleration, we know the distance traveled in the y direction from A to B. So which can we use? Well, we know that, that's 0. We know that, we don't know that, and we want to find time, so we can't use that one. Again, we don't know the final y velocity, so we can't use that. Here we know that's 0, we know that, we want to find t, we know the y acceleration, and we want to find t. So there's only one unknown in here. It's in two places, but we can still use this equation. So this is the equation we want to use. And so okay, so that's 0 meters equal 7.25 meters. 7.25 meters per second times t plus 1/2 minus 9.8 meters per second squared t squared. Okay, so that's what we got to solve for t. So let's take this over to the other side. Let's just multiply this out. Now notice in this case we only have 2 terms, so we can just cancel a t. That makes it a pretty easy problem to solve. If there are other problems, if I started at a different height or ended at a different height, then there would be 3 terms in here, but we could still solve it for t using the quadratic formula, if you remember using that. But this makes it a little simpler. Okay, so let's solve this for t. So this is minus 7.25 meters per second over minus 4.9 meters per second squared. And the time turns out to be, let's see, 1.48 seconds. Now notice the units, meters per second over meters per second squared, gives you seconds, so the units come out to be what we expect, which is units of time. Okay, so that is the amount of time that it takes to go from point A to point B. And we've simply figured that out because we knew the initial y velocity, and we can calculate how long it takes to get back to the to y equals 0. So now we know time. So we can solve it in the x direction. And let's see, which things do we know in the x direction? We want to know x. We know the initial x velocity, we know the x acceleration, and we know time. So if you look right here, we can use this equation. We know time, we know the x acceleration, we know the initial x, and we want to find x. So that's the equation we're going to use. And this is 0, so this term goes to 0. So x is the initial x velocity, which is 3.38 meters per second, and time, which is 1.48 seconds. And that gives us, what does it give us? I think it's 5 meters. I didn't write, yes I did. 5.0 meters. Okay, so it's a bit complicated, but this is this two-dimensional kinematics problem for projectile motion. You'll use this numerous times in the lab exercise, and this will, if you haven't done this in lecture, this will be a good introduction to the use of these kinematic equations for two-dimensional kinematics in your lecture problems.